Welcome to another F769 Discovery Kit video. In this video, I'll be going over the audio BSP. Specifically, I will be bringing up the line in to line out pass-through. Unfortunately, the audio BSP that comes with the CUBE F7 for this board does not support line in, it only supports line out. But there is some help. The WM8994 codec driver does have support for line in, and the internet also has some helpful resources that I will use. First, I'm going to review the schematic and see what we have to work with. Then I will review the firmware that we have to work with. And then I will make the necessary modifications to get the line in to line out pass-through working. Alright, let's go over the schematic for the Discovery board. These schematics are in the appendix, and what I care about is the audio codec. You see the codec here. Let's identify the major pieces. It's good to start from the external and go in, or more general to more detailed. So here's the line in and line out jacks. You see the line in going into the input 1 negative terminal. So we have stereo here, and on the output side also have stereo. The codec also has speaker connections, which I won't be using, so making a note to disregard that in the firmware. This part's confusing. There are 4 MEMS microphones here. The interface to these is very simple. You clock them and they spit out the data. The clock is labeled DF-STM clock, and there's DF-STM data. This was confusing because the microphones don't connect to the codec, but they are shown as if they might be. Also in the BSP firmware, in the CUBE F7, the driver code for the microphones is in the same place, the same file, as the driver code for the 8994. That made me think that there was 8994 specific code to deal with the MEMS microphones. What I discovered later was that the other Discovery boards also have the MEMS microphones, so that's why they look like this. For example, here's the 7308 Discovery. We see that the microphones do connect to the codec. The 746 Discovery and the 7508 also does. Notice they all have the line in and line out connected. Back to the 769. So we have the SAI interface here. It's got the bit clock, frame sync, 2 data channels, and the master clock. Here's the I2C interface. The audio interrupt pin is not used for this application. Not sure what it does, maybe something with the microphones. On the microcontroller side it looks like this. Disclaimer, I'm not super familiar with the SAI or I2S, but that's okay. My approach is to know the desired result and figure out details as needed. Nevertheless, some understanding is required, and this diagram was helpful to me. This is from a ST training video. Here we see the SAI subblock A in master mode. It supplies the frame sync, bit clock, output data, and master clock to the codec. The SAI subblock B is in slave mode, and all it does is receive data in from the codec. Notice the 2 subblocks share the same clock. In other words, subblock B is internally synchronized with subblock A. And here we see how the clocks are connected. For this audio pass-through application, we're using SAI1, and both subblocks will use the same clock. The clock is selected from one of 4 sources, either one of the 3 PLLs or an external clock. The PLLs are sourced from one of these 3 system clocks. And here we have some constraints on the clocks. The frame sync is the same frequency as the sample rate, for example 48 kHz. The master clock has to be 256 times the frame sync, and we have a divider to use. The point is, the input clock frequency has to be chosen according to the desired frame sync frequency. Thankfully, the SAI HAL code will help us out here, and all we have to do is select the desired sampling rate and the input clock frequency. Just a peek at what's happening here. This function looks at the desired audio frequency, figures out what the input clock frequency is, and then selects the divider accordingly. And lastly, I want to point out that we will be configuring the SAI in free protocol mode, which will allow configuring all of these parameters. This document was quite helpful, even though it's for a different microcontroller. I'm assuming the IP block is exactly the same in the F7. Alright, now let's take a look at the code we have to work with. Here I am at the top of the CUBE F7, and first I'm going to look at the codec stuff. So I'll do a search here for codec stuff, anything starting with WM, and there's only one C and H file related to the codec. That's good. That means there's only one place to look for any code that has to do with the codec. Now I'll run through the driver code and reference the 8994 datasheet. The goal here is to see what the driver is doing and see how audio pass-through can work. Now I've decided to refrain from talking about how bad this code is, as that would take too long, and I think it makes sense to make a separate video just for that. Okay, here's the header. It says that we can do this stuff: initialize, set the volume, set the frequency, etc. The most important one is init, so let's just jump right in. The init function can initialize the codec for output, input, or both. It takes an initial volume level and the audio sampling rate. First it initializes the I2C, then it does errata workarounds. I could not find the errata description for the 8994, and these register addresses are not in the datasheet, so if anyone knows what these do, please share that information. Okay, first we have V-mid and bias current. We will see shortly that these line input channels are referenced to the mid-rail voltage, or V-mid. Here it shows the line input channels going into this input gain/enable stage, and also referenced to this buffered V-mid. Okay, register 39, 6C. So we don't want V-mid connected to ground. The startup bias current is how all of the analog circuitry works, so that's important to have enabled. Not to be confused with microphone bias. These are two different things, so ignore microphone bias, do not ignore bias current generator. And we will enable the V-mid buffer. Okay, here we have register 1, hex 13, for power management. Now don't forget to sanity check the endianness. If things make sense, your assumed endianness is probably right. Okay, let me get this right. An alternate bias current source, startup bias, is provided for pop-free startup. The startup bias is selected in place of the normal bias, so the first write to register 39 enables the startup bias current generator and selects the startup bias as the current source. The next write to register 1 enables the normal bias current. V-mid select will be 01 for two 40K dividers, and mic bias enable, don't care. Then it does a delay, I don't know, maybe for ramping up the V-mid. Okay, now configuring the output. You have a switch on the output device. Now I only care about the headphone. So first, register 5, enable the DACs. Register 5, 0303. Okay, DAC 1, left and right, enable. Okay. Enable analog interface 1, DAC 1, left and right, input path, time slot 0. What does that mean? Okay, here's the mixing diagram, the core or middle of the 8994 codec. We see the DACs here on the edge. These are enabled. And then we have these mixer paths, which are fixed paths. The DAC 1, left and right, are coming from this AIF1 DAC 1. So these two leftmost columns here. Following those down, it says here from AIF time slot 0, right and left. Okay, well what does that mean? Here we have the time slots and the channels. So the LR clock, or frame sync in SAI terms, switches between the left and right channels, and then within the left and right channels there is time slots 0 and 1. When we look at the big block diagram, it all comes together. Ignoring this DRC EQ 3D stuff, we see a clear path coming from DAC data, coming from the microcontroller, going through this mixer path to the DAC. Okay, moving on, the code says enable AIF 1 times slot 0 left to DAC 1 left mixer path. That's weird. I thought that's what just happened. Well, let's see. Register 601 and 602 hex 1. Enable AIF1 time slot 0 left to DAC 1. Yeah, that's exactly what I just described. I guess there's two enables, one for power and one for signal. I'm actually not sure. Either way, this is still making sense at a high level. So then we have disabling the left and right DAC. Okay, now scrolling down past the switch statement, the input configuration. Now, again, I only care about input line 1. Register 28 hex, value hex 11. In 1 are inverting input select. Okay, that programmable gain amplifier is shown here in the big block diagram. We can see that this PGA and the mixer after it is how the line input gets into the ADC. We can see that our input signal is routed to the inverting input. The non-inverting input is connected to V-mid, and we don't care about in 2. Next we have register 29 and 2A, value hex 35. Alright, record path, gain and mute. I'm not using the record path at all. It's shown here. You can send the DAC output back into the ADC and then send that ADC data back to the microcontroller. This was actually really annoying for me. Turns out if you don't mute this, the record path will be enabled, so there is no other enabling or muting besides this one. So you have to mute it. We have PGA output to mixer in mute, so unmuted, and then output to the mixer gain. Yikes, 30 dB. Why on earth would you want 1000x power on an audio signal? Please, somebody give me an explanation. So at this point I want to shout out to this guy, JRP, for discovering this first and giving me the hint that I really should go through the driver. Also, this project does sort of work for line in to line out. In the later part of this video, I'm going to significantly improve this code. Next is register 4, value hex 0303. So enable the left and right ADCs. Now, same deal here as before. The block diagram is unclear, but at a high level, the ADC data is going to AIF1 time slot 0 left and right. Interesting, both the DAC and ADC data are coming from, we're going to AIF1 time slot 0 left and right. Okay, registers 606 and 607, same thing here, enabling the mixer path, still unclear. And DRC1 GPIO pin, going to ignore that. Moving right along, clock configurations. Audio frequency 48K, register 210. So this sets the sample rate, obviously. What's interesting is that this happens automatically. On the first page it says that frequency locked loops provide all of the necessary clocks for all standard sample rates. Also interesting is that the sample rate of the ADCs and DACs is independent from the rate at which the I2S data is clocked in and out. Not sure though, I'd have to experiment and learn something. Moving along, register 300, value 4010 hex. The upper half, 40, is all defaults here. So we can swap the left and right ADC channels. We can tri-state the ADC data when not transmitting. We can invert clock polarities. The I2S timing is not fixed. Polarities can be inverted to match the microcontroller. And the lower half says 16-bit word length, I2S format. Register 301 is not written in the driver. It's left to the default. Scanning through this, nothing very interesting. Register 302, all zeros. These are defaults. Set it to slave mode. We're not in master mode. Register 208, 0A. So we're enabling the processing clock and digital mixing clock. DSP clock. Not using any DSP functions, but whatever, just enable it. Register 200, the AIF1 clock, setting the source to M clock 1. That's coming from the microcontroller. and we're enabling it. Alright, registers 2D and 2E. We are connecting the headphone out amplifier to the DAC1 directly. So that's nice. We are bypassing all of this mess, and here connecting the headphone out volume directly to the DAC. And we see here everything having to do with mixers can be muted, don't care, and the same thing for the DAC1 right channel. Cold startup, if this is the first time being initialized, variable here stores the state. Run this cold startup sequence, otherwise run the warm startup sequence. The 8994 comes with default control sequences, and you just make a write to one of the registers to run the sequence. It doesn't really matter to me at this point. I just want to get the thing to work. Dang, this is getting old. Soft unmute the mixer path. So there is DAC mute, mixer mute, headphone mute, input mute. Did I miss any? More speaker stuff here, gonna ignore that. Here we have register 1 written again. The charge pump is required when using the headphone outputs. It is not possible to bypass the headphone amplifier, and the line out pins are not exposed on the Discovery board. Unfortunate. Anyway, this register 51 says to use the analog interface 1 DAC time slot 0 for the charge pump, and to use the Wolfson Class W charge pump controller, which uses less power. Wow, yet another write to register 1, this time ORing entire 16-bit values together, one of which is exactly the same value that was just written 2 writes ago, and then OR equaled to some variable. Such brilliant code. Anyway, it's enabling the headphone outputs. Enable headphone intermediate stages? Oh, what now? Oh, it doesn't even do anything, but you're required to set it 20 microseconds after enabling. Great. At least it's spelled out in sequence here. Alright, enabling the charge pump. It's bit 15 of this register, with some wacky default values. I don't know why you couldn't just write a 1 to bit 15 instead of keeping all the other bits. Alright, what are they doing? Writing register 2D again, with all zeros and a 1. Oh no, they're rerouting the DAC output to go through the mixer, even though they had previously bypassed the mixer. So now it goes through the mixer and unmutes the path. See here, before the DAC was bypassed to go straight to this amplifier, but now it's going through the mixer. Just awful. And then they enable the output mixer here. Okay, enabling the DC servo and doing the startup, and doing the startup servo mode here. The servo circuit removes DC offset from the headphone outputs, and doing the startup sequence does some measuring to make this happen, and it takes 86 milliseconds per channel, hence the following delay. Whatever, I'm not designing an iPhone, I just wanted line in to line out. Okay, back to register 60 here, and now the EEs set everything here to 1, which is now finally removing this short. I guess they're shorted by default to avoid clicks and pops. Yay, finally at the end, just unmuting a bunch of stuff. I'll just trust that they got all of them there. Alright, and now at the end we have this volume control, and then some more disable muting here, and high pass filter. Done with that, finally. Okay, now we can move on to the firmware part. First, working with what the ST CUBE F7 gives us, I will demonstrate outputting a square wave. This will reveal how we deal with the buffers when implementing the pass-through, in other words, copying the input to the output. Then we'll see that the entirety of the SAI input side is not available to us in the CUBE F7. These 3 lines is how I will output the square wave. We see here I have a playback buffer of 1024 samples, and each sample is a signed 16-bit integer. I'm going to fill up my buffer with a square wave, assuming these are actual 48 kHz samples. So 480 samples in 100 Hz, toggle every 240 samples. The magnitude is 30,000, or roughly the max amplitude of a 16-bit signed integer, and the buffer is filled up toggling between positive and negative 30,000. Then the BSP audio out init configures the SAI input clock as discussed before, does the MSP init for GPIOs, DMA, enabling clocks, initializes the SAI output, then resets the codec and initializes the codec. BSP audio out play calls codec play, which doesn't do anything besides unmute, and it's already unmuted, and then it calls the DMA transmit. The data type of this buffer and the size are critical. I'll get back to that. Alright, let's build and load it. What do we expect? First I'll point out the probe connections to this 1/8 inch stereo jack breakout coming from the line out on the Discovery board. Well, there's a square wave, but notice the period is 2.5 divisions at 1 millisecond, which is 2.5 milliseconds, or 400 Hertz, 4 times the expected frequency. Why is that? That's because I filled up the buffer with samples, but the DMA transmits SAI frames, not samples. We'll see in the code that the SAI frame is 64 bits, containing both left and right channels, so this was way off. First, what I want is a conversion between sample buffers and SAI frame buffers. Here's the SAI output configuration. We see some settings: master mode, TX, stereo mode, 16-bit data, free protocol mode, 64-bit frame length. So here in the conversion function, remember that one SAI frame is one audio sample. So one sample is 64 bits of frame data, or 8 bytes. So the DMA buffer length in bytes is 8 times the number of samples. In the loop, we're traversing the DMA buffer in steps of 8 bytes, and setting a 16-bit pointer. The sample is inserted there. Then the 16-bit pointer is incremented by 2, in other words, advancing 4 bytes, and the same sample is inserted there. In other words, it's filling up the left and right stereo channels. I replaced the call to BSP audio out play with the call to HAL SAI transmit DMA, so I can control the parameters, instead of using the nonsensical STM BSP API. In order to do this, I've temporarily declared the extern SAI handle, which is defined in the audio BSP. Later I'll organize my code so it is completely independent of the audio BSP. Now, the DMA transmit, it takes a pointer, obviously, but the size is not in bytes. The size is the number of whatever size the DMA was configured at, or M size and P size. In this case, it's 16 bits. So this is the number of 16-bit M sizes. Notice I have this SAI DMA transmit buffer, which is the actual frame data going to the SAI. As I said before, its size in bytes is 8 times the number of samples, and the size of the DMA transfer is the buffer size in units of M sizes. This is assuming we're transmitting the entire buffer. So now if I rebuild and load, we get this. Zooming out a bit here, we see 10 millisecond period, or 100 Hertz. Good. Now that I have the transmitter working properly, I can bring up the receiver. First I'm going to factor all this out into a new C and H file, or module as I'll call it, so it's nice and clean, and I can confidently remove dependencies on the audio BSP. Okay, now everything is under this function, my audio init in my audio.c. Start clean, stay clean. Let's remove this BSP audio dependency now while it's easy. This will prevent us from accidentally adding another reference to it later. So first I need to replace this call to BSP audio out init. This is easy. All it does is configure the clocks for SAI, MSP init, SAI out init, and codec init. So I'm just copying stuff in, following the Boy Scout rule and cleaning up a little bit every time I visit. Here I've removed the pointless parameters to clock config and removed the nonsense from the name. It has nothing to do with in or out, it's clocking the SAI peripheral. BSP audio out, MSP init, removing the handle parameter and this pointless instance check. Obviously the instance is the audio out SAI instance. This function does nothing but initialize the audio out SAI instance. Now here's mine. And here the DMA linking can now take the address of the actual SAI handle, not a pointless pointer to it. Now the SAI handle has to be defined somewhere, so I'll just define a new one here instead of using the extern one from the audio BSP. The SAI X out init is actually fine. I have no problem with this. I just copied that in. Okay, next I can remove this ridiculous attempt at polymorphism. This BSP only supports one codec. Why are you checking which one it is? And we can replace these 21 lines with one and call the driver init function directly, adapting the parameter names over like so. Okay, now I can remove the dependency. I'm going to see a bunch of undefined symbols and macros, so I'll just bring those in, no problem. Okay, from the BSP audio.h file, we have SAI defines for instances, GPIOs, DMA config. This clock config function checks the frequency using defines from the 8994 codec header, even though it is configuring the SAI clock, and the codec can have a different sampling rate from the SAI frame sync frequency. If you could see my face, my palm would be on it. But whatever, we need the 8994 header anyway to call init. Lastly, the audio I2C address, a lonely symbol defined in the discovery.h header, where its only use in the entire codebase is in the BSP audio.c file. Now I have both palms on my face, and I will copy that in. Okay, I call it like so, and now I'll build and flash it again. And there it is. Alright, moving on. So just take my word for it, the CUBE F7 does not have any SAI initialization for the line input. There is input initialization, but only for SAI B or the DFSDM, not what we need. So rather than figuring it out, I used JRP's repo on GitHub. I'm going to follow that lead and bring up my own input initialization. And don't forget the Boy Scout rule. Here's the repo. Basically what I got out of this was removing the plus 30 dB gain on the inputs and muting the record path in the codec, and initializing the SAI input on the microcontroller. I will improve on this by cleaning it up and also creating a higher level interface for the copy buffer function, so we can deal with sample buffers instead of SAI frame buffers. Okay, first note that I've reconnected the scope probes to the frame sync and STB. This is the ADC data going out of the codec and into the microcontroller. Fortunately, there are test points on the board for this. We see a nice frame sync at 48 kHz, but no STB data. So the first thing I want to do is initialize the codec for line input and see some data on the line. To do this, we supply a parameter to the codec init. Here's the symbol, input device input line 1, and we see in the init function we are supposed to OR them together. Let's try that. Okay, we get data, but it's not the right data. These samples, I'm pretty sure, are not encoded. They're just signed 16-bit data, big endian, most significant bit first. In other words, human readable order. I'm not applying an input signal right now, and there's too much chatter on the line. I bet it's because of that 30 dB gain and or record path being enabled. So let's change these register values to 20, which will take away the plus 30 dB and mute the record path. And let's try that again. Okay, that looks better. Now notice the difference when I apply an input signal on and off. We see more significant bits going high, but only on one of the channels. I believe this is because I damaged my board by hooking up scope probes directly onto the line input jack, and that's why I have the breakout board now. So now I know for sure there is data going into the microcontroller, I can more confidently continue. To complete the pass-through, I still need the following things: MSP init and SAI init. I'll copy and paste those from the JSP repo. DMA receive, I have to figure out the buffer sizes like I did for transmitting. I have to redefine the interrupts, some of which are part of the existing CUBE F7 demo project code. There are 3 levels of interrupt callbacks, which is annoying. There's the ISR itself, the HAL handler, then the application handler, in this case the BSP handler, and in there, finally some flag is set, and then the application has to read it and do something. Then lastly, I will improve the copy buffer function to give sample buffers to the application programmer instead of making them deal with SII frames. Okay, I'm going to bring in the input MSP init from the JSP repo. Now what I've done is removed the audio interrupt stuff because that's not necessary. I believe the ISR is not even defined in the JSP repo. I've removed the SAI instance check, and I've defined a SAI input handle, and I've brought in the input defines from the header file. And I can call it like so, and I've brought the codec initialization to below the SAI initialization. Okay, now for the input SAI initialization. Man, this just annoys me so much. Why do people just insert code in places and not make functions or modules? I blame it on crap IDEs that put up so much resistance for you to write decent code, and an over-reliance on tools like CUBE MX, which scare you into submission. People, it's not that hard to do this stuff without the vendor holding your hand. Yeah, for some reason it's easier to say, oh, I can just copy and paste this stuff here because I want this code to execute at this point in the program. At least it wasn't too much trouble to add that comment. Anyway, I'm just gonna delete this output stuff and leave the input stuff. Okay, now that I have the initialization in there, I can call HAL SAI receive DMA. For this, I need a DMA receive buffer for received frames. Oh, turns out this was pretty easy. Same size. Oh, whoops, I just realized this cast to unsigned int 8 is redundant. Okay, now I'll bring in this infinite loop from the JSP repo, which is very similar to, or exactly the same as the microphone to line out loopback projects in the CUBE F7. Here's the loop. It checks these volatile state variables to indicate the DMA receive buffer half full or full. The DMA is always writing to the buffer, so when it's half full, you get time to process the buffer while the other half is filling up. Don't need this max val thing, and this audio TX buffer state check is dead code, don't need that. It's almost like the only comments in this code base are ones that are redundant. This code clearly explains what it's doing, besides the names of the state enums. At least it explains what it's trying to do, as we'll see shortly. So I've cleaned up the loop here, and now, in order to set the volatile state variable, I need to hook up the ISRs and callbacks. Now here's the top level callback. So the next callback down is not in this file. Let's search for where this callback is called. Alright, it's in the bsp audio.c file. Okay, it's called here. Now where's the next level down? Okay, cplt callback. Okay, so this is called by the SAI DMA RX complete callback. Okay, and that callback is a field in this DMA handle. So let's see where that is now referenced. Ah, DMA. Okay, we see it called here, deep in some function. Ah, DMA IRQ handler. This looks like the bottom. And where is it? None other than right back up at the very top. Alright, let's grab those. Okay, I got my callbacks in. Let's run a build. Oh, I need to define that state enum. Okay, I brought that state enum in, and I've also commented out this part because it's complaining about these symbols here, which I'm gonna have to change them anyway. Okay, I get multiple definitions. That's because they're already defined in this demo project that I've started with, so let's get rid of those. Oh, I also have a RAM overflow. That's okay, I'll just make some more space somewhere. I'll start at the bottom. The ISR is defined in the it.c, DMA2 stream 1, comment that out. And the audio recorder app has the transfer complete and half transfer callbacks. Okay, here are those. I like this free RTOS message queue use. I'm going to actually use that later. And now I just have to clear up some RAM. Now there's many ways to do this, but I'm just going to scan through the linker map into the data section and find something that's big and not critical so I can delete it. Whoa, what is this? 40,000 hex? That's 256K. Okay, we see it's defined here, somehow used by the STM32F7 framework. I wonder if I can just change this to 128, and alright, it builds. But I'm still not quite done. I have to deal with this part. So this copy buffer function is saying the idea of what we want to do. When the DMA receive buffer is half full, copy the lower half of the receive buffer into the playback buffer, and when the DMA receive buffer is full, copy the upper half of the receive buffer into the playback buffer. And this will work if the only thing you are doing is audio pass-through, but any processing of these buffers won't work because you want to process buffers of sample data, not buffers of frame data. So we need the inverse of this function, convert sample buffer to DMA buffer, something like extract samples from DMA buffer. So in a similar fashion, this function will take the number of samples and it will advance the DMA buffer by 8 bytes and take 16 bits out of it. And we know we're getting half of a sample buffer's number of samples. And here's the copy sample buffer, basically just memcopy with 16-bit values. And then it's all put together here. Now I'm commenting this out for now because if I make a mistake in this part, it may screw up the other part. So I'm going to load this first and see if pass-through happens on half of the signal. Okay, great, it works. We see every other half is the 100 Hz square wave, and the other half is some music that I'm playing. So now I can add the other half of this loop. So when the buffer is full, extract half the total number of samples into the record buffer, starting at the middle of the DMA receive buffer, in other words, half the size of the DMA receive buffer in bytes. Then copy the top half of the record buffer into the top half of the playback buffer. Then convert half the total number of samples into the DMA transmit buffer, starting at the middle of the playback buffer, in other words, half the size of the playback buffer in samples. Explaining that was quite challenging, but I think the code pretty much speaks for itself. Finally made it to the end. This was by far the most difficult step in the platform bring-up, being that I wasn't familiar with SAI or the 8994 codec. Now it's all downhill, smooth sailing for the future. So note, this implementation of audio pass-through basically copies the buffer 3 times, which seems wasteful, but later we'll see how powerful the F7 is, and that linear time operations like buffer copies are not an issue. And now for fun, I can implement some easy guitar effects.